All right, hello everyone, Mr. Bozade here. I am going to go through the problems from the big formative, the LT5a problems. So you can hopefully use this to help yourself prepare for the summative. All right, let's dive in. So we've got, in problem one, we've got a 75 kilogram biker who is moving at 13 meters per second at the bottom of a tall hill. So the initial L corresponds to that time where he's moving at the bottom of the hill. Since he's at the bottom of the hill, we know his height is 0, so he's got no UG. But since he's moving, we know he's got kinetic energy. So I'm going to give him 3 units of kinetic energy. All right, going to come back up here. The biker applies 120 newtons of pedaling force forward while they ride along the first 12 meters of the hill. Okay, so this is going to tell us about our O, and because the biker's applying a force forward, we know that means there's energy going into the system. So we'll call that like work of force pedal. I'm just going to put like 1 unit of energy in there. Okay. At this point, so now I'm right here. At this point, the biker stops pedaling and is now traveling 8 meters per second. Okay. And so that's what our final L corresponds to when the biker stops pedaling and they're somewhat up this hill. So they are moving. We know they were going at 8 meters per second, so they have kinetic energy. And we know we're somewhat up the hill, so we've got some UG. So the energy needs to be split between the two. We do know that he's going slower than at the bottom of the hill. At the bottom of the hill, he was going 13 meters per second. Now he's going 8 meters per second. So I'm going to give him less kinetic energy at the end than he had at the start. So he had 3 at the start, so let's just give him 2 at the end. Okay. So now the question is, how much UG should he have? Well, energy is conserved, meaning the total energy needs to be accounted for. So if we had 3 units of energy here and 0 there, and we had 1 added in, then that should equal 4. So we've got 2 here, so there needs to be 2 here. So we'll put 2 units of energy in UG. Now, one thing I always say in my class is that once you've got that LOL diagram done correctly, that is oftentimes the hardest part of the problem, because now we're just going to follow through here and we're going to kind of get our equation, plug in our numbers, and solve. So we know we've got kinetic energy in our first L. We've got plus work force pedal, and then we've got kinetic energy plus UG at the end. So in our equations are 1/2 mv squared plus force pedal times distance equals 1/2 mv squared plus mgh. Now we plug in our values. I think this could be considered the next somewhat difficult step in the problem. So we know that the mass of the person is 75 kilograms. So let's see here. So we got 1/2 times 75 kilograms times, and his initial velocity is 13 meters per second, 13. And don't forget to square that, plus force push times distance. The force of his pedal actually is 120, so 120 times the distance, which is 12 meters. Okay, equals, and over here we got 1/2. His mass is 75 kilograms. His velocity at the kind of partial way up the hill is 8 meters per second, so times 8, don't forget to square it, plus mgh, 75 times 9.8, and the height is our unknown. 9.8, and then the height is our unknown. Let me just scooch this over like so, and then we can squeeze the h in there as our unknown. Okay, so we multiply these things together, and this 1/2 times 75 times 13 squared is 6,337.5. 120 times 12 is 1,440. 1/2 times 75 times 8 squared is 2,400. And 75 times 9.8 is 735, and that h is still there. So now that's a first step I always take, multiply everything together that I can. Now I'm going to combine these two. So those two add up to be 7,777.5 equals 2,400 plus 735H. Now I'm going to subtract my 2,400 to the other side. This is our first kind of real example of algebra. Since these two things are added, I'm going to subtract it over. So I get, when I subtract those two from each other, I get 5,377.5 equals 735H. And since the 735 and the height are multiplied, we need to divide both sides by 735. And we find that the height is 7.32. Don't forget your units. Height we measure in meters. So 7.32 meters is the height of the hill at the second point. Now this one, I will admit, is the hardest question in LT5a because it has so many different types of energy, right? We've got kinetic at the beginning, work in the middle, kinetic and UG at the end, okay? But like I said, if you get that LOL right, take your time with that, then things go easier from there. If you get the LOL right, these steps are pretty easy, the energy types and the variables. And then it's all plugging numbers can be a little challenging, but after you get those numbers plugged in, it's all algebra. All right, let's try the second one of LT5a. All right, 1,600 kilogram roller coaster car is moving at the top of the first hill. All right, so the initial is the top of the first hill, and we know that it is moving. So we know it's got height and kinetic. So I'm just going to give each of them 2. Since it has height, it has UG. It's got a height of 9 meters to be exact. Assume the track is frictionless. So that is telling me that there's no work done by friction in this O. And air resistance is negligible. Again, that's just kind of reiterating that there's no friction. And there's nobody's pushing this car, so there's no friction, so there's no work out, but there's also no push or engine or motor, so there's no work in. The car, so now I'm right here, the car has just enough energy to make it to the top of the second hill at a height of 14 meters with no speed. That's super important. If at the second hill it has no speed, then we know it's got no kinetic energy. So how much UG should I give it here? Let's just do our conservation of energy just to see. We've got 2 units plus 2 units plus nothing equals 0 plus, all right, so it's got to be 4, right? Because we have 4 over here, so we got to have 4 over there. So let's say the UG has 4. That's conservation of energy right there. As I always say, once you get that LOL done, if you get that right, then it gets easier from there. So now we've got K plus UG plus 0 equals UG. So that's 1/2 mv squared is our kinetic energy equation. mgh is our UG equation, and mgh. Now we just got to plug in numbers. The mass, as we see up top, is 1,600. So we got 1/2 times 1,600 times the velocity at the top is, as you can see, let me just clear this up a little bit. The velocity at the top is, we don't know. Is that what we're solving? Oh yeah, we're solving for that. It's velocity at the top of the first hill. So we've got the height. So this is v squared, that's our question mark, plus, so now we're going to go to our mgh over here. The mass we know is 1,600. Gravity on Earth, the gravitational field is 9.8 newtons per kilogram. And there we go, the height is 9 meters. Okay, so then plus 0, we don't even have to put that, equals mgh of the second hill. Again, we know the mass is 1,600 kilograms. Gravity on Earth, the gravitational field is 9.8. And we see that the height of the second hill is 14 meters. 14. All right, so now we multiply out what we can. 1/2 of 1,600 is 800, so we got 800 v squared. Multiply these things together, and we get 141,120. And multiply these things together, and we get 219,520. So since these two are added, I got to move this to the other side. I'm going to subtract it to the other side. So when I take 219,520 and I subtract off 141,120, I'm left with 78,400. And so we still, on this side, we still have 800 v squared equals that. So then since these are multiplied, to move the 800 over, we need to do the opposite. We need to divide by 800. So divide both sides by 800. And we see that v squared equals 98. And then finally, we got a square root. And the square root of 98 is 9.9. So the velocity equals 9.9. Always remember to put your units on there. And velocity is meters per second. Again, I always say, once you get that LOL done, it gets easier from there. So put your time into it. Take your time. Make sure you get it done well, because these two steps are easy, and then plugging in the numbers is a little difficult, and then it's all algebra after that. All right, let's look at our last problem here. 0.4 kilogram soccer ball is released from rest at the top of a hill that is 7 meters long. Okay, so we're at the top of a hill, and we're released from rest. So we know there's no velocity, so there's no kinetic energy, but we're at the top of a hill, so we got some UG, right? That's our initial is at the top of the hill. The ball experiences a friction force of 0.6 newtons while it rolls down the slope. So we know friction is trying to slow the ball down, so there's going to be work transferring energy out, work of force friction. How much do we want to transfer out? 1, 2, or all three? That's a question mark. Let's read on to see if there's any energy in that last L before we decide. The initial location is when the ball is released at the top of the hill, and the final location is when the ball reaches the bottom of the hill. Well, at the bottom of the hill, the ball is still moving, so there's definitely some kinetic energy. So we do not want this work of friction to take all the energy out, just some of it, so maybe 1 unit. So let's see how much is left. We got 0 plus 3 minus 1 equals, so there's 2 units of energy. We know there's, at the bottom of the hill, our height is 0, so there's no UG. So that means the kinetic energy must be 2, like this, okay? Now that we've got our LOL done, it should get easier from here. We know we've got UG minus work of force friction equals K plus UG. So that's MGH minus force friction times distance equals 1/2 mv squared plus mgh. Now we just got to plug in our values. All right, we know the mass of the soccer ball is 0.4, so 0.4 kilograms times gravitational field on Earth, 9.8 newtons per kilogram. And the height of the first hill, it starts at a hill that's 7 meters tall, so 7 meters. Minus, you know, the force of friction is 0.6 newtons, and the slope has a length of 12 meters, so 0.6 newtons times 12 meters equals 1/2 mv squared. The mass is 0.4. The velocity at the bottom is what we're solving for, right? We're finding the ball's velocity at the bottom, so that's just, we're going to leave that as v squared. That's our question mark, our unknown. And, well, what the heck here, guys? There's no UG. What was I thinking? Nothing's there, right? So let's just make that go away. No UG, no UG. Sorry about that. All right, so that, but the good news is that makes our problem easier. Alrighty, so let's wrap this up. So let's see. So now we plug in our values, and what we see is this right here, 0.4 times 9.8 times 7 is 27.44. Minus 0.6 times 12 is 7.2 equals 1/2 of 0.4 is 0.2 v squared. Take the difference of these two over here, and we get 20.24 equals 0.2 v squared. Since these are multiplied, I'm going to divide the 0.2 over, and I get 101.2 equals v squared. And we still need to square root both sides, and when we do that, we get 10 meters per second is the velocity. All right, there you go, folks. Those are all the problems of LT5a from that formative. I hope that helps you prepare for the summative. Good luck. Bye.